Hi everyone, I am Alankar Datta, a graduate student in the Department of Physics at Indian Institute of Science. I work in the Computational Astrophysics group with Professor Prateek Sharma. In this video, I'll briefly talk about our recent publication submitted to MNRS and also posted on arXiv. In this work, we try to build a simple analytic model of local gas structures produced as a result of strong radiative cooling around cold clumps of gas in the circumgalactic medium. Typically in literature, cooling flows are considered for halos as a whole, for example, cooling of large clusters of galaxies. But we show that such flows can also explain the gas properties in and around small-scale clouds embedded in a diffuse medium. The details of our model is as follows. Let's consider a small overdense region, shown in blue, in a surrounding medium of hot gas, which is shown in red. Then this overdense region, because of its very high density, quickly cools through a very efficient radiative cooling. Because it loses its internal energy so fast, this region loses its pressure balance. Consequently, the hot gas, which is at high pressure, flows along the pressure gradient to this overdense region. This gives rise to what we call as local cooling flows around cold clouds in the CGM. Mathematically, our model is a system of coupled differential equations. It is important to note here that to build this very simplified picture, we assume that the cold clouds follow cylindrical or spherical symmetry. We also assume that the pressure gradients due to cooling as the only driving force moving the gas around and neglect all other physical effects like turbulent mixing or gravity. Our models are very similar to Bondi models of accretion or Parker wind, except that it's now cooling driven instead of gravity. What we are interested in is not the dynamical situation, but the end steady state of cooling flow. Let me elaborate a little more on this. The motivation is that the cold clumps can be seeded in an otherwise hot diffuse medium by various physical processes like thermal instability or turbulent mixing. However, irrespective of the diverse origin of these cold clumps, at some point of their evolution, if dynamic effects saturates, then these clumps are left with small pressure gradients which cause a constant steady inflow of gas from the hot diffuse environment into this cold structure through continuous radiative cooling. These are precisely the systems which we had in mind while building this model. Then we try to see how far such a naive modeling can go in explaining virtually similar but more complicated simulation data. More on this later. We identify that the solutions of a cooling flow model can be broadly classified into two distinct physically acceptable class of solutions, the transonic solution and the subsonic solution. Additionally, the cold gas can have large magnetic fields in them due to flux stressing. Therefore, we include a very simplistic treatment of magnetic fields in our model by treating the magnetic field as an additional polytropic fluid, reducing pressure in addition to the gas pressure present in the system. If you are more interested, I would encourage you to have a look at the detailed analysis presented in our paper. We also test our steady-state solutions against time-dependent numerical solutions generated using Pluto, which is a finite volume hydrodynamics code. To test the limits of our solutions, we compare it with the more realistic simulations of the CGM from the Elasticity TNG cosmological simulations. Nelson et al. 2020 identified cold clumps of gas in the hot diffuse CGM. We try to match the stack profiles of these cold clumps with our model-generated steady profiles. As you can see in this figure, this match is not very impressive with the simulation data. However, one must note that our solutions are extremely simple-minded and the reality is far more complicated. The whole point of this work is not to explain these simulations in rigorous detail, but to qualitatively understand the dominating physical effect that is in play. We also derive an analytical expression relating the energy lost by gas due to cooling with its Bernoulli number and the mass inflow rate due to steady radiative cooling. Such a relation as this has observational importance as emission from the CGM is an observable characteristic. However, this classic cooling flow relation should be applied with caution as we show that it is only applicable within a very limited range of temperature phases where radiative cooling is very fast. At all other phases which lies beyond the local environment of the cold clouds, turbulent mixing dominates the phase evolution of the gas, causing significant deviations from a steady-state cooling flow model. On this note, I would like to conclude saying that our cooling flow model only highlights some of the key physical effects that generate local gas flows in and around cold clouds. However, further work is needed to explore the physics and observational implications of the interplay of cooling and turbulence in the circumgalactic medium, both in the diffuse phase and also in the radiative boundary layers around these cold clouds. Thank you for your time and attention. Please subscribe to our channel if you would like to hear more about various astrophysical simulation related works like this from different members of our group.